What are you seeing on the Zoom? Are you seeing full screen?
Yes, full screen.
Good.
No.
Oh, is it?
Yeah.
How about
Yeah.
that? Okay. And now we're.
You want to bring your laptop
I can-
down here, Scott?
I can mirror it. Hang on, let me.
Better come down with your laptop.
I think if I mirror it, it should be. I think.
Yeah,
That's hard.
Okay, there is nothing. Okay, good.
Connect to that. Yes. Oops.
You prefer to read your file?
Still one or the other. Yeah, I think I have to do it. PowerPoint. I have to tell it. Yeah. I think if I need to tell it to mirror and just mirror whatever I've got here. How do I do that?
Is it not from the Zoom end if you just tell it to capture the whole screen?
I tried that and it was. Okay, let me try again. Okay, that needs to. That needs to flip. Why is that still showing it like that?
I think if you right click when you have and you press show presenter view when you're presenting. So right click and then say
Swap displays. That's there.
and then what's on
So I need to share my screen too on Zoom. I think. That one, right?
yeah, if not, then that one. I think that one probably should be the one.
That works?
Yeah, that's
Yeah, we're there.
Yeah, very nice.
Good. Well done.
Yeah, yes.
Complicated doing online plus in person.
yeah. Hybrid is surprisingly not as simple.
Oh, that seems so. Do you need charging? Or you
Should be okay.
Okay.
Fully charged. I've got a charger, but it kicks off.
Yeah, thanks for making the venue change.
Yeah, no problem.
The lecture theatre and the fully booked. So
Yeah, okay, yes, yeah. That's okay. It's good to come in.
But it's difficult to.
It's just
Many scientists are West Cambridge, but then
Yeah.
more central for the undergrad. So it's a bit
Yeah,
of a
it's yeah.
Postgrad scientists versus undergrad.
that's true. Yeah.
And we have both in the committee as well.
Okay. Do you alternate or something? Or
Maybe we might try doing an event.
Yeah.
We haven't decided yet for Laura's whether Laura's also
Okay, great.
talk,
Yeah.
whether to do that in West or here.
Yeah.
I think for now we're going to do it here. Sorry. It's good how you had automatically set up the Zoom, which is great.
Yeah, okay. All right, let's get started. Hello, everybody. Nice to see you here. This is the first talk of the term of QAds. Hopefully many more interesting talks to come and also socials. We've got the garden party coming up next Saturday, which should be pretty good. But yeah, I'll hand it over to Joseph to introduce our speaker. And thank you very much, Sam Stranks, for agreeing to talk here today.
no problem.
Looking forward to it. All right.
Thank you, everyone. So Sam Stranks is professor of Optoelectronics and the Royal Society University Research Fellow in the Department of Chemical Engineering and Biotechnology and the Cavendish Laboratory, University of Cambridge. He established his research group, StranksLab, in Cambridge in 2017, with a focus on the optical and electronic properties of emerging semiconductors, including halide perovskites, carbon allotropes, and organic semiconductors for low-cost electronics applications, such as photovoltaics and lighting. Sam completed his PhD at the Rhodes Scholar at Oxford University, receiving the 2012 Institute of Physics Roy Thesis Prize. In 2016, he was named a TED Fellow, and in 2017, he was listed by the MIT Technology Review as one of the 35 under 35 innovators in Europe. Sam is also a co-founder of Swift Solar, a startup developing lightweight perovskite PV panels. Can we put our hands together for Professor Sam Stranks?
Thank you. Well, thank you very much for having me here. Thank you for the introduction. It's fantastic to be here and to kick off your series this term. And welcome back to Cambridge as well. I'm sure it's been a very busy start to term for you all. So I will talk, I hope that the mic's working okay. Yeah. I'm going to talk today about our work on perovskite solar cells and where it fits in, particularly into decarbonizing electricity. It's an emerging technology that's coming out of the lab, but we're starting to see the first commercial products. So it's a very exciting time to be working in this space and also to hear about where it's going. So I want to first just contextualize PV and the potential PV has to really provide a lot of electrical power for us. If this cube represents how much sunlight's hitting the Earth, so the power hitting the Earth at any one time, then this is our global power demand. You can see solar it's a huge resource. In principle, could well and truly cover what we need, and even our growing power demands. And these are our current PV installations. So we're at 1 terawatt. This is a fantastic achievement. To be fair, we've been rolling out PV very, very rapidly over the last decade, and in particular over the last few years. So there is a lot of PV, but there is a long way to go. And I'll talk about that throughout this talk. So the cost of PV is already competitive in many places. This is a plot that shows the levelized cost of electricity of various energy technologies. And so here we're plotting the cost of electricity. This is US data, but we see similar things in many other countries as well. And in blue, these are different PV technologies, and you can see that particularly utility scale PV is competitive with many of the other more traditional energy sources. And of course, the lower the cost we can make solar PV, the more it can contribute to decarbonization and energy solutions. Of course, a disclaimer here that LCOE doesn't account for intermittency. It's a very important point. I'm not going to cover that so much in this talk, but that is a bigger and wider discussion. It's also it's going to be a critical part of our energy solutions, in particular for decarbonizing. So here, this is looking at the carbon intensity of, again, various technologies, looking at from coal and gas all the way through to the renewables, PV and wind. And you can see PV is overall very low carbon intensity. There is some carbon, of course, put into manufacturing the PV panels, particularly the silicon panels, but in the end, with a lifetime of these panels of 30 years, well and truly pays off, and it puts it in a very low carbon region. There's also, so we can think about public health benefits as well through better air quality, so replacing a lot of the traditional fossil fuel technologies with PV and other renewables as well, or other technologies that don't produce emissions. So just one study, this is showing that if 27% of PV generation was in the US was from PV by 2050, it would lead to $167 million in health benefits alone, and save 60,000 lives. So it's not an insignificant number. And of course, that if we scale that across the world, it's a huge amount of money and also lives saved in doing so. The other interesting aspect is thinking about energy security, energy equality. This is something that's becoming a growing issue, particularly over the last summer. We've seen real issues in particularly energy security. When you think about sunlight, if you average over the years, the sunniest country, Azerbaijan, is actually it gets 4 times more sunlight than the cloudiest country, which is Norway, and that's a factor of 4. So that's a very low discrepancy when we compare that to something like uranium. So thinking about the resources of uranium, there's 1,000 times variation between those with the most resource and those with the least resource. And when you think about oil, it's 1,000,000 times from those with the highest resource of oil to those with the lowest. So it really is a leveler in this sense in terms of the resource. And on top of that, the lower GDP countries tend to get more sunlight on average than richer countries. So again, it's a leveler and really can be thought of in terms of equality. So this, I think this is a really interesting plot and somewhat surprising, I think, when we think about how good the IEA should be. So this is the International Energy Agency every year puts out predictions for how much PV will be deployed. And that's shown in these dashed lines here. So this is each year they put this out, and the dashed lines show the prediction. These data points here show the actual observed deployment. And you can see every year continuously they underpredict by far how much PV will be deployed in that given year. The IEA tend to be quite conservative with their estimates, but still it's in many ways, in many years, there's a huge discrepancy. And in fact, this trend has actually continued. I can update this plot. This has actually continued still. We're still producing and still deploying more solar than the experts can predict, which is a very good thing for when we think about decarbonizing and climate change. So solar deployment is growing very fast, and it's a very good thing. And the real driver for this is cost. So if we think about the cost of a PV module, this is the cost of a PV module, so dollars per watt, essentially $17 per watt over the last 30 or 40 years. The PV module price has dropped a factor of 100 since 1980, and and about 10 times since 2010. So in the last decade alone, it's dropped a factor of 10. And this is fantastic. Something in particular, this last drop, this was not precedented at the time in 2010. So this has really driven this wave of deployment, and really why solar PV is much cheaper and arguably more affordable than it was even only a few years ago. The driver for this is cost reductions in the raw materials and manufacturing. So think about economies of scale. We're producing more and more PV panels, and that means everything comes down in cost. And the other aspect is the lab R&D work that has really driven the efficiency up of these cells, the reliability up of these cells and these modules. And so a lot of the cost reductions is credited to this as well. And it's these two factors that have led to this crash in price. But the current PV technologies won't get us all the way there. There will be a limit to how far and how much we can deploy this technology. And I'll talk about in a few moments the workhorse technology, or the market is dominated by crystalline silicon cells. These are very good technologies, are very efficient and very long-lived, and have been honed over decades. And the cost of those have come down. So this is the module cost. This is showing in Germany the cost per watt over the years. The module cost. So this is the panel itself, the PV panel itself, and how that's dropped in price from the arguments I showed in the previous slide. But there's a whole lot of other costs with the PV system that need to be thought of. These balance of systems costs. So this is the wiring, the installation, the inverters, and in fact, this is now dominating the cost of solar. So, and in fact, when we take this plot forward, the module cost has continued to come down, but the balance of systems cost has remained steady at something like $1 per watt, or a bit just under $1 per watt. And this is an issue because it means the PV system cost is now dominated by these balance of systems costs, which are much harder to bring down. Cost of installation, the cost of wiring, inverters, all this, the cost it's very difficult to bring these down. And the second limitation of silicon is that we have to produce them and process them at very high temperature. So typically to temperatures of 1,000 degrees Celsius or more to produce a very highly purified crystalline silicon ingots that are then made into the cells. So this means it's energy intensive, well, at least relatively energy intensive. It also limits our rate of deployment. You have to build very large factories that can process these modules. You don't have the modularity of building, for example, smaller factories. And also limits the applications, and I'll talk a bit about that. So most PV panels we deploy on rooftops or solar farms, but we're pretty much limited to those applications. The other side to that is, and this is seen more recently over the last year or two, is really the geopolitical and supply chain uncertainties. In fact, even from COVID, we've seen over the last 2 years that the cost reductions that we've seen have actually plateaued a bit because of supply chain problems. And it's unclear how long that's going to last, and that will have a dent and an impact on how fast we're deploying these PV technologies. The geopolitical aspects as well, because PV panels are made in only a few countries around the world, in 2 countries essentially. Germany has some manufacturing, but most of it's in China, and there'll be uncertainty over some of the supply chains. And also, in fact, the US, for example, have imposed tariffs on some of the panels coming in from China. And so there's some real uncertainties there going forward. And there's some arguments for being able to at least diversify manufacturing so that there are more places around the world fabricating and manufacturing PV panels. So we really need solutions with higher efficiency. Remember that higher efficiency of the system of the PV panels brings down the cost of the entire system, including the balance of systems cost, more modularity in how we make them, and also how we use them, reduce costs, and then also new manufacturing paradigms, even thinking about faster manufacturing as well, rather than these very complicated heating, high temperature processes. So just to unpack silicon or a solar PV system. So these are the workhorse systems. You see these on rooftops, you see them in solar farms. These are crystalline silicon panels. They're, as I said, a very good technology that's been honed for decades. If we break it down into what they are, so the way they're made, there's ingots of silicon, these large essentially cubes of silicon that are cut into cells, or that are basically silicon wafers. These solar cells are then strung together to make a module, and that's the panels you see on rooftops are the individual panels. These are the modules, and then these modules are then strung together to make arrays. And typically in a solar farm, for example, like this one here, that's a solar array. In some other technologies, and there are some commercial technologies, thin film technologies, where instead of having to make cells because of the limitation of ingots, you can deposit the film across the entire module directly. That's essentially a monolithic module. This is another approach, and then these modules can then be strung together to make an array. If we look at break that down, the actual panel itself, so you have the solar cells and solar module, there's typically encapsulation sheets on either side, and then glass and frame to close out the actual panel. So in terms of thinking about operation then of a solar panel or a solar cell, so at its heart, or at its simplest, what we have is some semiconducting material that's able to absorb light and absorb light as strongly as possible. And then we energize electrons and also energize holes as well. So where the absence of an electron, we have to consider that as a moving particle. We generate electrons and holes, and then these electrons and holes are taken to the electrodes and collected as current. Because you're driving the charges to either side, you generate a photovoltage, and we're also generating a photocurrent. So because we've got photocurrent and voltage, we're getting power out from that cell. So just to put that here, so we absorb the light, the sunlight coming in, and then these electrons and holes are transported to these electrodes. And so we need to think about things like how well we can make that semiconductor absorb the light, how well we can transport those charges to the electrodes without them hitting, for example, defects and traps. And I'll talk a bit about that. Some of the work we're doing, and how we can maximize the efficiency of these processes. When we think about what the semiconductor is, we have to think about the solar spectrum. So what is hitting the Earth? What is the solar spectrum that's coming in? So this is what the solar spectrum looks like. We have the space spectrum here. What is of relevance for most PV panels, which most of them are terrestrial, is this spectrum here. So you do have some absorption from moisture and other molecules in the atmosphere. So we need to optimize light harvesting to collect this spectrum here. When we think about the semiconductor, the semiconductor will have a given band gap. When we come in with low energy photons, so red light, for example, so this light out here, there won't be enough energy to energize electrons. So in fact, those photons will pass through, and we won't be able to harvest any useful electrical power from that. And so a lot of this light here, in fact, for most semiconductors is lost. We can't actually harvest that for useful power. But if we come in with blue lights, higher energy light, we can energize well and truly above the band gap and energize electrons and holes, which we can then collect at the electrodes. Just as a note here, though, because we've given it excess energy, all of this energy is lost to heat, because these electrons are excited to high energy states, and then it relaxes down, and we lose some energy to heat. So there's inevitably some losses in this process to be able to harvest as many photons as we can. I'll speak about that in just now. So we need to think about, so we want this band gap to be as small as possible to be able to absorb as many different energy photons as we can. So one would argue that we should have a small band gap to do that. And so you can think about, this is looking at the current density of a solar cell. and looking at the absorption onset, or in other words, the energy decreasing. And as we decrease the band gap, you can see the photocurrent of the cell goes up. And that's all well and good. We do lose some of the excess energy above the band gap to heat, but that's inevitable. But the problem is when we think about the open circuit voltage, which is the other aspect of the solar cell, we need as wide a band gap as possible, because essentially the open circuit voltage, or the maximum we can get, is dictated by the band gap, and in fact dictated by the difference in quasi-Fermi levels splitting between the electrons and holes. So this leads to a compromise. So we need to maximize the products to get power. So what we have is we end up having an efficiency maximum at a particular band gap, which is somewhere about 1.1 EV, or up to 1.3 EV, depending on some of the calculations, which is actually not far off where silicon is. Silicon's a bit lower than that. And the maximum efficiency is about 33%. So this is the thermodynamic limit of how much sunlight can be converted to electricity. And we can't get over that. We can't get around that unless we design devices in other ways. It's not violating any thermodynamics. It just means we're using other ways to harvest sunlight. So remember that 33% is the absolute theoretical limit. I'll show this plot here. This is I'm not going to go through in depth, but this is to show the different PV technologies that have been worked on around the world. This is showing that this is actually, so the National Renewable Energy Lab, so the NREL US produces plot and update it regularly. These are the best research cell efficiencies. They're certified results of different technologies. So looking at the efficiency over the years, and each color stream is a different PV technology. So what we see in blue here, this is silicon. Here, these red curves here are some of the emerging technologies. So organic solar cells and other ones, they're less efficient, but they're also more recent. They're only really coming on the chart a decade ago or so. This red and yellow one is actually the perovskite. I'm going to talk about that in a few moments, but just to show that there is this huge collection of different technologies. At the top here, these are multi-junction technologies where we're layering 4 or even 5 different absorbers together. You can go up to very high efficiency here, but they're extremely expensive. They're typically using 3-5 semiconductors, and most of these are limited to space applications where cost is not really an issue, but they're not viable, unfortunately, for terrestrial applications. So I mentioned emerging materials, and this is a key point. So if we think about perhaps more traditional semiconductors, and so this plot on this end here, traditional semiconductors tend to be much simpler materials. That they're, for example, crystalline silicon or 3-5, so gallium arsenide. Semiconductors, the unit cell is relatively simple, at least in a relative sense compared to some of the other materials. And these are wafer-based technologies. The thin film technologies using generally other technologies, other semiconductors. So here we're just replacing the semiconductors. There's some of these, the CIGS and cadmium telluride are both commercial thin film technologies that are at volume and actually making reasonable headway in the market. And then these much more emerging technologies. So the perovskite I'll talk about here, but even up to quantum dots, and some of you may well work on quantum dots and use them. These get much more complex. So when you think about the structures and the disorder in these materials, they are more complex. But generally, the trend is that these are simpler to process. So they can be cheaper, much cheaper, but generally they're lower efficiency because they are more disordered. Whereas here, these are much more complex to process, but they are simpler materials. And so what we ideally want is something that can perform really well, but it is simple to process and cheap. So that brings us on to the halide perovskite materials, and just to say what a perovskite is. So a perovskite is a huge family of materials called perovskites. They're anything that takes the ABX3 crystal structure. It's one of the most abundant minerals in the earth, in fact, at least the mineral version of these, particularly minerals like calcium titanate. But the materials we're working on for PV applications and other applications are halide perovskites, and they typically have in the A site an organic cation, so methyl ammonium or an inorganic cation, cesium, so they're typically small cations. In the B site, there's typically a metal, so lead or tin. There's some other metals being used as well, and X site is a halide. These are essentially human-made minerals. They're not found naturally occurring. We make them in the lab, and they're very different than the minerals that we find in the Earth crust, other than sharing the same crystal structure. So this is really why they're creating a lot of excitement. This is the efficiency gain, or efficiency we've seen over the last decade. This is silicon here. You can see the perovskite. The perovskite has really shot up, and in fact now is, at least at the cell level, is almost as efficient as silicon. And I won't be surprised if in the next year or so this will overtake or at least match silicon. As a note, I've put the efficiency limit 30% here. This is really more the practical efficiency limit for cells. It's not the thermodynamic limit, but it really is where we can push some of these to without using other adaptions. Really, one of the most exciting things about these materials is it has opened up a new world of very tunable semiconductors that are very crude. We can process crudely, but they're very high performing, and that has really been a paradigm shift in semiconductor technologies, where and as I showed in the previous slide, where we're taught we have to make a semiconductor very, very perfectly crystalline, have no defects to make it perform well. And this material is actually rewriting that a bit. In fact, in many ways, some of the more disordered versions of these perovskites actually perform better than the more ordered versions. So it's a very interesting from a technological point of view, but also from a scientific point of view, that we're seeing this new class of materials that rips up the textbook in many ways. So how we process them, this is what we do in the lab. So typically we dissolve the ionic precursors in solvents and essentially make inks, and we cast them down onto these substrates and spin coat them in the lab at a few thousand RPM. So it spins and forms these very uniform crystalline films, which are yellow here, and then we heat them at 100 degrees Celsius, which is quite a low temperature for semiconductor processing, at least. Remember the 1,000 degrees that silicon would need. But by doing that, we form these very nice crystalline films, and this is the PV absorber that we use in our solar cells. Because they can be processed at low temperature, what it does, it opens up manufacturing on different substrates, and this is actually an example. Instead of manufacturing on glass, for example, or on other substrates, this is on a plastic foil, and you can also do this on metal foils as well, where this is a roll-to-roll printer, where this is the precursor solution, a precursor film here, and then it's heated to form this crystalline film. And so this opens up really high throughput manufacturing. You can think about roll-to-roll newsprinters essentially making solar cells, which is really exciting and something that's, again, a very big paradigm shift from what we can do with silicon cells. As a note here, I'm not going to talk about so much, but because of this manufacturing, this paradigm shift, one could think about much smaller factories and more modular factories built around the world. There's an argument for perovskite cells to actually be able to be deployed and manufactured, in particularly in lower middle income countries. We've actually got a case study going at the moment, working with researchers in Ethiopia as well, in Bahir Dar University, to investigate manufacturing in Ethiopia. And I'll happily discuss that in some of the questions. In terms of why they're operating very well, so these materials, they absorb light really well, but they're extremely thin. So if we look at crystalline silicon, so a typical crystalline silicon cell is about 180 or 200 microns thick. It has to be extremely thick. And this is because silicon actually doesn't absorb light very well. It's got an indirect band gap. So effectively, you need a very thick slab to be able to absorb the light very well. Whereas we look at the thin film technologies, and this is where they get the name, thin film technologies, cadmium telluride, it's something about 2 to 4 micrometers thick in thickness. And to harvest the same amount of light, the perovskites are 500 nanometers thick. So they're extremely thin. In fact, this is, for reference here, human hair is 100 microns. The red blood cell is 7 microns. This is the PV cell, just how thin it is. And so this is why it opens up applications in lightweight PV, and why, for example, crystalline silicon cells typically are quite heavy and bulky in comparison. The other thing we can do is tune the chemistry of these materials and actually tune properties like the band gap and tune the color of these absorbers. So this is an example where this is actually changing the halides from a pure iodide system and mixing in some bromides to move to a pure bromide system. And this opens up applications in building integrated photovoltaics. We can think about designing the PV cells into the building, and rather than something that you put on the rooftop and try and hide or put in a solar farm. So it's actually quite interesting, again, paradigm shift. These are less efficient, of course, because we're tuning the band gap away from the optimum, but this is this is an inevitable penalty we may have to pay to make them look good, for example, if one wanted them integrated into a building. But it also opens up new surface areas that you can use for PV. Where I see the really exciting applications is in tandem photovoltaics. I mentioned briefly about the multi-junctions where you could make many cells together and get a higher efficiency. This is a specific case where you layer two together. This is a tandem solar cell. So here, the top cell harvests the blue wavelengths, and then the red light passes through. It's not absorbed by the white gap cell, but it's absorbed by the bottom cell. And in doing this in tandem, you can get above this thermodynamic limit that's limited for a single junction. You can get around that when you use two junctions here. And so in terms of a practical efficiency target, silicon itself is about 28%. That's where it's going to hit practical efficiency limit. The perovskite tandem PV, you can move to 35%. And that doesn't seem like very much if you think about efficiencies, but if you think about these operating for 30 years, there's a huge amount of energy, much more energy being produced by a cell operating with this efficiency. And also with the knife edge economics of PV, it is very much a step change in this. There's also arguments of energy payback times. If you think about energy payback times, it can come down significantly because it's much less energy put into making these panels because of the lower temperature, and also greenhouse gas emission factors. When you think about this, it really does drive down a lot of these sustainability metrics. One other configuration of these tandems, and this is actually one of the first commercial products, in fact, is actually layering the perovskite on top of silicon. So here, this is essentially taking the existing technology and coating another perovskite cell on top. And by doing this, you can effectively boost the efficiency of the current silicon technology. And this is something that a company called Optoelectronics is commercializing, and there's some very early products coming out now, which is quite exciting. Just to touch on the lightweight aspects, and particularly the high power lightweight aspects, and putting these tandems into as lightweight cells. Here you can make this as a flexible solar cell that's very lightweight. This opens up a number of new applications. So looking at a cheaper installation, for example, so having a roll of solar that can roll out on a rooftop this can be much cheaper than the racking of panels that is done today with silicon panels. There's applications in space and also aerial communications. One of the really fast-moving application spaces is putting them in the rooftop of electric vehicles, so boosting the range of EVs. All of these applications here require high watts per kilogram because you don't want to be adding any extra weight. So this is why the high performance and lightweight cells can be really important. I've co-founded a company, Swift Solar, it's based in California, to commercialize some of these lightweight and high performance aspects. I'll happily talk a bit more about that as well. So the other aspect, I've talked a bit about efficiency, but the other aspect is reliability of these cells and durability. How long will they last? And it's a very difficult question because to prove it can last for 25 years, you really have to put it out in the field for 25 years, but we don't have that time. There's some industry standard accelerated tests that are done to really stress them as much as possible and replicate that as much as possible. And they're looking very promising over the last 2 to 3 years. We've seen some really good improvements here in stability of these cells. These are just a few examples, and in fact, there are several others even that have come out in recent weeks that are months, which are really exciting. So this is over 2,000 hours running the cells at 70 to 75 degrees Celsius under continuous operation and continuous sunlight round the clock. And what you can see is here is in red, this efficiency, it really isn't dropping at all. See very, very little drop in performance, which is very encouraging. It's not saying it's going to last for decades yet, but it is a very promising step along the way. This is a year testing and again, under high stress, and there's very little drop in performance. And this is actually mini modules. These are slightly scaled up versions, so about this size here, 30 by 30 centimeters. And again, even though it's lower efficiency, it is surviving and passing all these tests. So this is very promising, but still a long way to go here, and I'll talk about that for the last part of the talk. But I did say, I mentioned that there's some early stages of commercialization now, so there's quite exciting things happening. So Oxford PV, I mentioned they have a They have a pilot line, production line, in fact, in Brandenburg in Germany. Semiconductor in China also has a manufacturing line, and there's some products coming out from Solar Technologies. In fact, this is one of the first commercial products that was out. This is a solar blind that was produced by Solar in last year, and where Swift is also moving quickly towards some first products. So I want to just in the last part of the talk really talk about the challenges, and I've given quite a rosy view of the technology. I want to make sure it's clear there are still challenges to take this from the lab to commercial space. These are 3 challenges I picked. There are others as well, but I think these are probably I'd say the grand challenges that really need to be shown. I just want to say this is our research group, and we are focusing on a lot of these challenges. We're based in chemical engineering and biotechnology. This is us at our research day last year. In fact, we have this year's one tomorrow. This is us at Clare. We do a lot of photophysics in our experiments, so I have to give the obligatory ground state and excited state photo. This is us. I'll do that. See the progression. So that's us in our excited state. In fact, this is us in our excited state. A few weeks ago, we were at the research. We were a group trip away in the Lake District. We've got some lovely weather. Fortunately, this is us in our very excited state. Very high. But so what we do, a lot of what we do is we do laser spectroscopy, and we use photophysics to try and understand these materials and understand where power losses are, how long, for example, energized electrons live before they recombine or before they hit defects, for example, and lose their energy to heat. So we use a lot of fast laser spectroscopy to understand these things. One of the particular techniques we use is actually luminescence. So it's a bit counterintuitive, but we actually we shine light on a solar cell and look at the light coming out. And that's something, it sounds counterintuitive to look at light coming out of the solar cell, but actually it tells you a lot of very instructive bits of information. And the reason is because any semiconductor, if we energize it, excite electrons, eventually those electrons will relax back to the ground state and typically emit a photon. And we can detect that photon coming out, that light. But what will happen is that if there's traps there or defect states, then these electrons will instead hit one of these defects. They essentially get trapped, physically trapped in one of these states, and then they lose their energy to heat, and therefore we don't get a photon out there. So this means we can use this to assess where there's traps and where and what samples have traps, because we want to maximize the light coming out from these solar cells. So in fact, it's counterintuitive, but a good solar cell should actually also be a good LED. We should be able to put electricity in and get light out. And in fact, we use this reciprocity very frequently in our labs. One example of where we've used the spectroscopy, this is what we want to do is look at how far and how long these charges travel before they recombine and lose their energy or be collected. Here, this is a cross-section of a perovskite of a half device, in fact, with one electrode. And what we do is we energize these electrons and holes, and we do an experiment where we don't have an electrode there, and these electrons and holes will move about and eventually find each other and emit light. And so if we can do an experiment where we put a pulse of light in, and then we look at the light coming out over time. This is in nanoseconds, so this is a very, very fast experiment. And then we do another experiment where we put an electrode on, and we now have an additional boundary condition, essentially, where when those electrons hit that interface, they're lost to the system. And so what that means is there's a very fast quenching of that emission. So we can model when we have these electrodes. In fact, we can then model this with a diffusion equation and globally model this with and without the boundary condition here, and extract diffusion lengths from this. And what we found is that these charges can travel at least a micron before they recombine. And that's important because this is about 500 nanometers thick. What it means is if we create energized electron here, it means it can traverse this entire distance and be collected without losing its energy. And that means we can make very thin solar cells and they can work. And so that was a really important finding. It also means we don't have to think about more complicated ways of collecting the charges, which we see in, for example, organic solar cells or other technologies where the fusion lengths aren't as long. We've also been looking at these techniques in microscopes and looking at the light coming out from these. So we look at devices and look at the energized electrons and then look at the light coming out. This is a photoluminescence map. So essentially the light coming out with a spatial map. These films typically are polycrystalline, so they're made up of these very small grains, mosaic grains. And what we see is some of these grains are really dark and poor, they don't emit much light. So remember, these are the ones that have lots of defects in them, and the other regions are really bright and emissive. And this is what we want. We ideally want a uniformly bright image here. And so there's some very interesting power losses here that we're trying to get rid of, and I'll talk about that as well. We're also doing this with tandem cells. This is actually perovskite textured. So silicon often is textured to increase light absorption. This is actually the perovskite coated on top of silicon. And there's also some very interesting variation there as well. I won't go into that into too much detail on that. One of the quite interesting things with these materials is that and I alluded to it earlier, that we see lots of disorder in these materials. And this is quite interesting. This is a different electron microscope images zooming in gradually to higher and higher resolution all the way to here. And what we see is on all the different length scales, we see disorder. We see lots of variations. So this is really zoomed in here. You can see even a lot of these grains we find are actually made up of smaller subgrains and smaller crystallites. And again, this really opens the fundamental question: why do these work so well, even though they are so disordered and so heterogeneous in their properties? It's a very interesting question. It's still ongoing, I'd say. What we've seen is also that those luminescence maps I showed, that what we find is actually there's really small defect clusters that are scattered around the films. So they're really tiny, about tens of nanometers in size. They're not entire grains that are full of defects. They're just small clusters that are spotted around the film. And what we see is actually these little clusters, these directly relate to where we have luminescence losses. So this is a map. The color map is showing the photoluminescence. Remember the light coming out. And what we see is where we see the dark regions, so the black regions, we see these defect clusters appearing. So these defect clusters are problematic for these power losses. We can also actually visualize this trapping process. So this is actually this is a technique where it's essentially a photo emission technique in an electron microscope, and we excite with a very fast pulse of light. And what I'm going to show here is when we get to 0 picoseconds, that's when the light comes, you're going to see carriers trapping in these tiny trap clusters. So these dark regions here are where these energized carriers are trapping. So it's a really the technique is fantastic. We can really start to see now on very, very small length scales and very fast time scales these carriers trapping, and this is essentially leading to a loss in the solar cell. It's something we need to get rid of. What we find, just to sort of tie up this section, is what we find that these small nanoscale trap clusters are actually related to other phases of not things that aren't perovskite. So we can look with very, very sensitive electron microscopy techniques, and most of these grains here are perovskite. We can index them. We can look at the crystal structure and find that they're perovskite. But these shaded yellow ones, these are actually other structures that are not perovskite and are problematic. And even though they're really tiny, they end up being quite problematic for the cell. I just want to show one example where these phases are really problematic, and this is actually looking at before and after long-term illumination. So we're illuminating the sample over time and looking at the same scan area. And what we see is where you see these defective regions, so shaded in yellow, what we see is afterwards we've got material loss there, and we're starting to see degradation of these specific sites associated with those with these shaded regions. And we can see that also this is another example here. We can see where these yellow regions are. Afterwards, we're seeing material loss at these sites. And I'll give one more example where we see this interface here. We see these problematic phase impurities, and afterwards we see that that's degraded. But actually here we're starting to see that the perovskite is also starting to be eaten away as well. So what this is telling us that these really tiny trap clusters, these are really problematic for degradation as well and stability of these cells. That's something we really have to remove, both for performance but also for reliability of these materials. Just some examples of where we've been able to heal some of these defects and these traps. So here we've been using different additives and post treatments to to make these maps much more uniform. You can see that here, these dark grains have really brightened quite significantly, and this is promising again for processing and for processing much higher performing films. We've also been adding in some different additives. So this is an example where we add potassium into the sample, and what we see, this is a cross section of the cell. We see that the potassium decorates the grain boundaries, and in fact, these interact with some of these defects and actually passivate those trap states, and we see a good performance increase in the solar cell as well. I talked about the challenge of scaling up. A lot of these cells that we make are relatively small. They're about 2.5 by 2.5 centimeters, about 1 inch square, so this size in the lab. A big challenge is, of course, to take that to then mini module and then to full module size. Recently, we've been actually looking at vapor deposition of these samples. So here we're vapor depositing, so we sublime the materials onto the substrate, and you form really uniform films in that way, and also you can do that with a very large area. So this is an example of a very uniform, flexible film that we've recently produced, and this is actually producing, although the efficiencies are still a bit lower than the solution process versions, they are catching up very quickly, and this is a very scalable technique that can be is very compatible with high throughput manufacturing as well. And then this is our recent work on the tandems, the perovskite tandem solar cells. This is looking at, remember where we have the wider gap cell and then the lower gap cell, and this is a cross section here, and we've got some really nice results now. This is a 24% tandem, which is one of the best in the world, in fact, for these all perovskite tandem solar cells. And this is again, this efficiency is ramping up very quickly as well. Remember, we can practically get to something like 35%. There is still a nice window to go up even higher. And then maybe I'll just skip over that just for time. I talked mostly about PV. I'm just going to finish to say that we're also working on other applications with these materials, and actually, if we make them much thicker, we can actually really nicely attenuate X-rays. And we've got some very exciting projects on medical imaging with these in X-ray detectors, and here the idea is that you can make much more sensitive X-ray detectors that could bring X-ray scanning or CT scanning down to very low dose. And this opens up really a lot of early stage disease diagnosis as well. If you can more frequently scan and with more sensitivity, this could be a very good thing. Displays and lighting, I haven't talked so much about that, but we're also working on them for different colored emitters and white light. So you can think about, again, flexible form factors can be translated to the lighting. And finally, some of the mobile solar water pumps. So this is some work we're doing with, again, with Bahidar University in Ethiopia, to make mobile solar water pumps where you can move these lightweight panels around the farm. And so instead of doing very tedious and backbreaking manual pumping of water, smallholder farmers can use these solar water pumps. And we were actually there a few weeks ago, and this is we've got a small prototype now starting to be demonstrated in the field. And then finally, we have in the group we've actually found a charity, SustainEd, which is developing teaching resources for primary school teachers. So this is aimed particularly at year 5s and 6s, where we're developing modules that are not just teaching that there is a climate change problem, but there are also solutions to this problem. This is now getting kids doing hands-on activities, but also to teach them about the fact that there are solutions to climate change, which is actually a surprising gap in the curriculum. They're taught about that there is a problem, but not that there are solutions. And I'll happily talk more about that. So just to summarize, these perovskites I see them as being able to take the baton on silicon. So we need silicon to keep ramping up as much as possible. The perovskite technology really is the next gen technology that then can take us really from 2030 to 2050 and as fast as we can. With that, thank you very much. I'll thank my group and various collaborators who've contributed to the work I've presented today, and happily take questions. Thank you.
Thank you very much, Sam. We have this fancy
We've got the box
that we can pass around if there's questions in the crowd, and I really hope there are. We want this to be like a forum where you can ask questions. There are no dumb questions. That's my philosophy. So, do you have any questions in the crowd? Yeah.
Thank you. Thank you for the presentation. I was just wondering about the colored
Yep.
So to what extent is the efficiency loss when you put color?
Yep. So good question. So the best perovskite cells I showed, or at least the records, are 26%. When you move to the sort of yellow ones, they're more like 10 to 12%, something like that. So you are seeing quite a drop in efficiency. In fact, even when you think about maybe we can actually go back to that efficiency plot with band gap. There's quite a few back. Yeah. So you can actually see the drop off as you move. So 2 EV on the right there is somewhere in the sort of yellow absorption region. So it's dropping off to sort of 10 to 15% at its absolute best. So you do pay a penalty, but it might be, if you can have PV in more places, it's a penalty worth paying.
This actually links to the other person's question.
Yep.
How does that depend? Because you're pretty much not replacing buildings or replacing it for, I don't know, glass, etc. You're kind of replacing glass with padding. Does that kind of cost compare to what you then put on, so you're actually getting energy out the matter, but you're still paying approximately the same amount?
Yeah, so that's the idea, that you could eventually you could make your glass and add a PV panel at a fraction of a cost more. It's not there yet. I mean, it means that there is some building integrated PV industry, and it's growing, but it would still be much cheaper to buy glass and just put glass up. But longer term, things like and the other thing, it's not just colored. You can also make semi-transparent glass. These things are applications that are quite exciting. The problem with the building integrated is, of course, it needs new builds essentially to go up. It's much harder to retrofit, and that means it's the rate new builds go up is not high enough to make a huge impact. There's also just on that, there's an interesting company, Ubiquitous Solar, who are making completely transparent glass PV, and there you'd harvest light in the UV and the near infrared only. That means the visible is transparent, and they're actually making quite good progress, and it looks like they've got some nice products on the market already. So that's quite exciting, I think.
I was wondering if you could elaborate a bit on what the theories are for why the kind of disordered microstructure is beneficial.
Yes, yeah, good question. So the microstructure I showed is this. So there's two bits of disorder. There's structural disorder, which is kind of as you move around, the crystal structure changes a bit. That seems to be problematic. There's another disorder, which is chemical disorder, and actually as you move, I could show some of those maps, but as you move across, there's actually chemical variations, for example, in the halide content. And what we find is that what that does is it actually gives a little bit of band gap variation across the film. And so carriers can actually funnel down to the lowest band gap. And in those regions, they recombine very radiatively. And even if there's traps there, it means you can, because you've got very high carrier densities, you can saturate those traps. So it's quite a complicated mechanism, but we're starting to get a handle on it. The other thing is this funneling allows carriers to move away from where the traps are. The funneling actually draws carriers to other regions where there aren't traps. So it's mostly the chemical heterogeneity, I would say, but it's complicated and hard to harness and to make sure there's a gain, or at least to maximize the gain.
Sorry, I'm not from a science background, so a lot of over my head, but really exciting talk. I've got a question about your experience in Ethiopia.
Yep.
And the possibility of factories.
Is it me or?
The possibility of building modular factories in
Yes.
countries. What was your experience? Did you have to import in a lot of expertise or materials or the resources already available to you?
So I would caveat where it's a very early stage, so we're at discussion stage effectively. There's two parts to that. One is we've got this solar water pump project, and we've got a sort of small prototype that we're starting to develop. But in parallel to that, we're looking at larger energy manufacturing. The conversation we've had, in fact, that was the end of September, we met with a few of the ministers from the Department of Energy there. They're very interested, and there's some really exciting conversations, but they're very early stage. I think there's two things. One is the technology is still being translated from lab to fab, or lab to sort of scale up. So there still needs a bit of time before we can build a factory. But we do have to start sowing the seeds now, to really look ahead. So realistically, it'd be 5 years before the first modular factory might be able to be built, and maybe 10 years before there's perhaps multiple and at scale. But it's an interesting conversation. It's something that is very new world to me of thinking about large scale manufacturing and in different countries. It slides well, I think, isn't it?
First, thank you for the comment. Exciting. I was wondering, tying back into those a bit of like the larger scope. So when compared to like silicon panels, I think one of the remaining sort of environmental problems with the kind of chemicals that are used in processing and that are put into panels. If I remember correctly, sometimes those chemicals can leak into the ground and be very toxic to the environment. So have you looked into kind of a comparison between silicon and perovskites?
So yeah, so we certainly are thinking about these things. There's some issues. So with silicon panels, in fact, in the solder there is lead in the solder of silicon panels, and that can be an issue that can leach out. Although it's quite well contained, in fact, in the encapsulation. The perovskites do have, for example, lead in them. It's very small amounts when you think about these extremely thin films, but we are thinking about particularly encapsulation methods to package them well and make sure that they can survive, even if there's catastrophic failure, there won't be any leakage. And it also raises the interesting question about recycling the panels at the end as well. It actually really motivates doing that even more, that we really need to, at the end of life, think about how much we can reuse the panel, but also just securing it, making sure it's not taken into landfill. There is a big problem, and probably many of you know, in PV, that I think it's going to be 50 megatons of PV waste by 2050, just the panels that are reach the end of life and they'll just be put in landfill because they can't be recycled. So there's an opportunity with this new technology to actually build it so it's recyclable. It contains its elements while it's operating, but then it can be unpacked at the end and recycled. So we've got some early work on some of those aspects.
Just a quick question regarding the cost comparison between silicon and
Yep.
potential perovskite. I know it's in the early stage, so that might not be quite accurate yet, but what is the kind of like cost of the like going to be?
Yes, so there certainly are, yeah. So a lot of the cost projections have to rely on volume and other things like that. If you think so silicon, if we think about module costs, silicon's predicted to get to about 10 cents per watt for module cost, which is extremely cheap and actually amazing. Perovskites probably won't go much lower than that on the module cost, just because you end up hitting a cap of in terms of materials. But efficiency is really where then it can come in. So the efficiency going from, even though so we can get a little bit lower on the module, but the overall system will then be cheaper. In terms of numbers, there's predictions of silicon coming to, I think it's 4 cents per kilowatt hour, and the perovskites could get to about 3. So it's quite sizable, but it's there are still some uncertainties in that. But that is with the higher efficiency.
What is it at the moment?
Perovskites?
Yeah.
Not enough to be on the chart, I'd say, because the first products are just coming online. Most of those are demo products. Silicon depends where you are, but it's about, I think, between 5 and 6. So it's pretty good, but there still will be room to come down further, and we need that as well because we do need more PV. Yeah.
If I may actually ask
Yeah.
a question, zooming out of it. If you remember one of your first slides about how much solar energy we could get from the sun versus how much it actually
Yes.
today.
Yeah.
I was wondering how much do you think realistically in the future we would want the amount that we're getting? You said it was 1 terawatt currently.
Yeah.
How much do you envisage that needs to become by 2050, for example, for net zero?
Yeah.
And what are the kind of I guess, the geopolitical issues, because you're saying it's possible,
Yeah.
but do you comment a bit on the geopolitical hurdles that could be overcome for us to actually achieve that final goal?
Yeah. So so the first, what was the first question? I think I lost in a second.
Like the 520.
Yeah, so it's a very good question. What it really relies on is the big question about storage, because if there was storage there, I would say 20 plus. The problem is with PV, if you're operating PV alone, it gets, once you're at about 20 or 30%, it starts to be, it's no longer viable to put more on, because you then either having some other baseload power that's getting more and more expensive that has to be on overnight, for example, or some other issues. So I think that's really the other aspect that I haven't spoken so much about, is the storage that really needs to come up, whether that's batteries or hydrogen or other mechanisms. We need that as well, really, to get to full decarbonization. And that's something that, I encourage you all working in battery technologies and other technologies to also keep working on these things, because we do need it to come along as well. But certainly, I mean, in terms of, the rate we're going with, last year there was, I think, 250 gigawatts of PV was put on. That's going to happen again this year, probably more. So we are going to get to the 2 terawatts much faster than we were. So we're going to get to multiple terawatts in the next few years, certainly in the next decade, without any step change. But if we can get storage on, then it motivates going even higher.
And in terms of the geopolitics, are there certain hurdles that you identify that if we overcame, we would give big breakthroughs?
Well,
you also hear this thing going around like, oh, if you took this many square kilometers of Morocco, you could.
Okay, in terms of where you put the panels, yeah.
Not Morocco, but like, just wonder what are your general.
Yeah, I mean, my view is, I mean, I think because there's, particularly in sort of North Africa, there was ideas to put a big solar farm, a solar array, but the transmission can be a problem. I mean, my view is having locally as much PV as you can is the way to do it. So having, and making use of solar farms and rooftops as well. The manufacturing is the other aspect to that. And I do think we need to diversify manufacturing, make sure that there is, more being made, but also it means there's an opportunity to bring high-tech manufacturing to many countries that don't have it currently.
I think we've run out of time for.
I'll say 2 more questions.
2 more questions.
Yes, go ahead. Yeah.
The first thing here, and then.
Is that me? I don't know if that's.
Thanks for the talk. I want to touch on things that have been asked a couple of questions ago about like material sourcing and extraction, because that's something in battery tech in quite a lot of hot water about cobalt mining. That is there any similar like issues for PVs, or is it a lot easier to source?
Yeah, good question. So most the materials being used for the perovskites, they're earth abundant. There's